Hello, everyone. Welcome to today's Skill Up series session. And I have one of our very own academic coaches, Rachel Brune. She is here today to discuss statistical analysis series. There's going to be a lot that she covers today. So I'm going to do some very brief housekeeping items for you. We are recording our session as usual. We will put this in the Graduate Studies Support Center. We welcome conversation in the chat. And of course, we also welcome questions in the Q&A function of your Zoom. We are in a meeting format. And of course, we would like for you to remain muted unless called upon. If you do have a question, you can raise your hand and we can ask to unmute if time permits, as Rachel pauses throughout her presentation for today. Okay, that about does it, Rachel. I think that covers my housekeeping items. I'm excited to learn from you, and thank you all for being here.
Yeah, thanks so much, Emily, for giving me the opportunity. And this is the first of hopefully a series of webinars where we're going to take kind of a deep dive into some of the common statistical tests. We get a lot of questions on these. So in this session, I'm just going to focus on the independent samples t-test. So we're going to be talking about when do we use this test, what are the assumptions of the test, how to conduct the test, and then interpreting the output that SPS gives us, and then reporting the results. Hopefully, we're going to get time to get through all of those. So let's talk about when we use the test. So we're going to use this when we're comparing two different groups of people on one continuous measure. We're looking to see if those two groups significantly differ on the dependent variable. So this would be like a comparison. We want to compare groups. So we have two groups, no more than two groups. If you have more than two groups, this is not the right test. There is a right test, but it's not this one. So we have only two groups of people. For the independent samples t-test, as I'm going to talk about here in a second, that is two different groups of people. And we're just looking to compare them on some continuous measure, meaning numerical. We're looking to see if their numbers differ on that value. So getting into our assumptions, the independent variable has to be a categorical variable with two levels. The dependent variable has to be continuous. There has to be an independence of observations, no outliers. The data must be normally distributed. There must be homogeneity of variances. And you're probably like, what do all those mean? We're going to talk about it. All right, so the independent variable. This is our grouping variable. So this variable has two levels. We can determine if this assumption is met simply by looking at how that variable has been operationalized. So something like, we'll go old school and say gender. Don't come at me. It's a good example. It doesn't really apply these days as much, especially if that's your field of specialty. But we're going with the basic male, female, two groups. I know that's not applicable today, but it provides a good starting point. This could also be like a yes, no delimitation. So do you own a BMW? Yes or no. That's two groups there. So as long as the way that the variable is operationalized, there are two groups, then it is an appropriate independent variable. This assumption is met. There is no test to determine if this is met. So our next assumption relates to our dependent variable. So again, this must be continuous, meaning that is an interval or ratio level of measurement. Again, numerical in nature with a meaningful numeric value. I'm not going to go too much into that one, but if you do have questions about determining whether it's interval or ratio or continuous, we can help with that in the Academic Success Center. There's also a group session on Thursdays. Again, this one is justified based on the operational definition of the variable. So if it's showing numbers, it's continuous. Independence of observations. Again, another one that we do not have a test for. It's based on how you conducted your study, how you assigned people into groups. So there is no relationship between observations within each group or between groups, meaning My two groups are made up of different people. They are not the same people. Independence within a group means that basically each person's responses were collected independently with nobody else around, so that person A could not influence person B. If you're doing like an online survey, this part of the assumption is probably a little bit implied. You're assuming that people took these without, working with their best friend and doing it on computers next to each other. And, oh, what did you put for this one, right? We're assuming that didn't happen. We're assuming that they took this independently. But this is a really common assumption. And again, it's based only on the design of the study. There is not a test to determine if this is met or not. All right, so outliers. This is for our continuous variable. So an outlier means that it's an unusually large or unusually small value. So it doesn't really fit the pattern of a majority of the data. We use a box and whisker plot a lot of times to identify outliers. So if you look at this box and whisker plot, the outlier would be that dot that's sitting above group one all by its lonesome. So you can see the box and whisker plot itself, that would be a majority of the data. And then there's that one value that doesn't really fit with the rest of them, and that is an outlier. We can also use the outlier labeling rule, which is finding the interquartile range and then multiplying that by 1.5. And then we would add that value to the upper quartile value and the lower quartile value. I'm going to demonstrate this later. So if you're not following that, no worries, we're going to get to it. So we want to make sure that both of these groups are free from outliers, and then we could say that this assumption has been met. Another assumption is the assumption of normality. So this is the idea that the values of the dependent variable are normally distributed. They form that bell-shaped curve for each group of the independent variable. We test this in a number of ways. So meaning we don't just look at one. So a lot of times I'll see students that'll just create a histogram. They're like, oh, looking at this histogram, it's met. So we typically have multiple points here to justify that it's normally distributed. And I will add here that the assumption is approximately normally distributed, meaning that it does not have to be perfectly normally distributed. And there's not really a rule on what is approximate enough or not. So part of that is up to your discretion. And again, that's going to come up when we work with our data set in a minute. So we'll talk about how to determine if it's okay to proceed, even if it doesn't appear to be perfectly normal. But we would do like a histogram, like what's shown. We can also provide a skewness and kurtosis value. I will have those again when we actually run the data, and I'll talk about those values a little bit more. The KS test, that's how we abbreviate it. It's the Kolmogorov-Smirnov test, KS test, or Shapiro-Wilks. We can use those to also help support our decision about this being normal or not normal, and then ultimately our QQ plots. And then our homogeneity of variances. So this is talking about the variability of the values for each group. We want that variability to be approximately equal, again, approximate. So we're looking at how much the data values vary for each group and comparing those. The Levine's test is kind of like a mini hypothesis test within the bigger hypothesis test. So this test has the null hypothesis that the variances are equal. The alternative is that they are not. So this is an instance, if you've been doing statistics, you probably have it ingrained in your head that like you want your significance to be less than 0.05, right? We want significant results. So I'm going to break that for this test and this test only, for a t-test at least, because there's other instances where this applies. But for homogeneity, for Levine's test, we do not want significance for this test. Because again, that means that the alternative is true, which means that the variances are not equal. And that's not our assumption. Our assumption is that they are. So we want non-significance. And I always remember in my head, for this Levine's test, significance means significantly different, and that violates the assumption. So we do not want significance here. So the big question, what do I do if my assumptions are violated? Great question. So you could consider doing some data adjustments. You could do transformations, bootstrapping. I'm not going to get into all of that for this. Again, we're trying to cover as much as possible. So we are going to do some adjustments. I am going to demonstrate how we could do that for one of the assumptions when we get to the data set. But there are a lot of options. So if your assumption is violated, you might want to do some research or work with a statistics coach to determine what options do I have? Like, am I just in trouble and I have to do a different test? Like, what are my options? So we can work and explore some of those options. We can also look at the robustness of the test to violation. Basically, what that means is like, yes, we assume that this is true, but if it's not true, how much flexibility do we have in that? So if my assumption of normality, if it's mostly normal, but just a little off, is that okay? So some tests are pretty robust on some of the assumptions, some of them are not. So again, doing a little research, working with a coach and exploring the extent of the violation and whether or not you can just go ahead and proceed with the understanding that there is a slight violation there. And then you could also consider just changing the test. So the t-test is a parametric test. As with most parametric tests, there is a non-parametric equivalent. For the independent samples t-test, that is the Mann-Whitney U-test. So if my data violates the assumptions, especially if it's multiple assumptions or if it's severe violations of the assumptions, then we could do the Mann-Whitney U instead. And that test doesn't have assumptions like normality and things like that. It works with ranking instead. So you could consider changing, which would mean getting familiar with the assumptions for that test and understanding the limitations of how you can interpret the results and things like that. Okay, before I jump into our data set, I want to pause for a minute and just see if there are any pertinent questions that have come up for me to touch on before we go on.
I'm just going to wait just a second or two, just to make sure. Again, if you do have a question, feel free to raise your hand or put it in the Q&A or the chat. I can keep an eye on all of those places. Happy to do that. Okay, so Rachel, I don't see any questions right now, but
no problem.
Okay.
Okay, so we are going to be using a data set that can actually be found in the library. If you've not learned about this database, I would encourage you to get familiar with it. So this is part of Sage Research Methods, specifically their data sets collection. So in that collection, they have data files that you can use, but also student guides that walk you through doing the test. So I'm using one of their data files, and we're going to go through the steps for conducting the independent samples t-test using this data file. But I just want to let you guys know this is available in the library, so you can also download the data set, you can download the student guide, and go through this on your own as well. So kind of practicing what we have applied here. So let me minimize this, and I have this data set open. I made this font size bigger, but I could not figure out an easy way of making the output window bigger. So the text size is what it is, and I apologize. So the first thing that we need to do is test our assumptions. So for this test, with this data set, it's designed so that we can compare our genders on their portion of fruits and vegetables that they eat. Before I jump into the test and the assumptions, I do want to kind of familiarize you with the data. So looking in this first column, this is the gender denotion for our participants. And we can see for this data set, they used only 2 identifiers for gender there. And then this is the portion of fruits and vegetables that each participant reports eating. If we go into our variable view, we can get an idea about the values. So if we go into our values column, we can actually look here And I can see, again, that 1 is male, 2 is female. All of these negative values would apply to participants that maybe refused to respond or indicated that they didn't know, things like that. So these would be considered like missing values or unknown values, and they give us that information in here as well. For our portions of fruits and vegetables, this applies only to the missing values. So this is how they handled any missing data. So we can look here, if we look in our measure column, we can see the level of measurement that's been assigned to each variable as well. So we can see that the sex variable is nominal, which is correct because we're classifying that, nothing more than just identifying. And then our portions of fruits and vegetables variable is scale, which is what SPSS considers continuous variables, meaning that it's numerical in nature because it's representing the number of servings, basically, or the number of portions that each person has been consuming. We will not be using the other 2 variables, so we don't really need to familiarize with those 2. So the first thing I need to do is check my assumptions. I already went through a couple of them, so checking those levels of measurement. So sex is obviously going to be my independent variable. It has 2 groups, male, female. And then my continuous dependent variable is that portions of fruit. So I'm looking to see, does the portions of fruit, the amount of fruit, basically fruits and veggies that people are eating, does that vary based on gender? Does gender affect the number of portions of fruits and vegetables that people eat? That is essentially the research question that would be driving this test. So I need to, I can also look at things like, are my groups independent? We're going to assume, and again, this is assuming, right? So this would be, if you're doing like your own research, this would be a section. You actually have a section where you're talking about the assumptions, limitations, things like that. So we are assuming that each participant only selected 1 gender. So each participant is only appearing in 1 group. We are also assuming that these participants completed this survey on their own without any influence from anybody else. So we need to test the other assumptions now. So the assumptions like the outliers, normality, homogeneity, things like that. So we're going to tackle the outliers first. So some things that we might do at this point is run like descriptive statistics. There are several options, and we're going to do a couple of them. I'm going to start with using explore. So for my dependent list, this is just going to be my dependent variable. In this analysis, I only have 1. Remember, our dependent is that continuous variable. So I can move that into my dependent list. The factor list is a really fancy way of asking for your independent variable. So I could place that here. And then I can click on statistics. Here I definitely want to check descriptives because that's going to give me a lot of this descriptive statistics that I want to look at. Typically, I don't use the other options. You can include things like the outliers, but it doesn't include all outliers. It's only like the 5 most extreme or something like that. So we're actually going to use a different method for identifying outliers. So we're just going to leave the descriptives box checked. Here we can also create plots. The stem and leaf is defaulted. You will almost never use that. Feel free to uncheck. You can include a histogram if you want. It would be a great starting point for evaluating that normality. We also want to check this normality plots with tests because remember, normality is one of our assumptions. So this is going to give us a lot of the tests and graphs that we need to evaluate if that assumption of normality has been met. So I'm also going to include that as well. For display, we can choose if we want to display only the statistics, only the plots, or if we want both. In this case, I want both because I need to see those numbers and I want to see the graphs. So we're going to run this, and this is going to help us determine if our assumptions are met. And SPSS, you'll notice it just left my spreadsheet and switched me over to the output window. So that's something important to know about SPSS, 2 windows there. So here is my output. Case processing, I'm basically going to ignore this. This is just looking at the number of points that were used in the analysis versus what was missing. I don't really need to worry about that as far as interpreting the assumptions and things like that, so we can ignore it. Our descriptives, this is our first view of the data. So what I'm going to look at here is just get a rough idea of something like normality. So does it seem like normality is met? So some things that I can look at the mean and the median. If these values are very similar, then that indicates that my data might be normally distributed. So I can see that 3.4 and 3.0, they're close, but they're not as close as I would like them to be, which tells me that we might be dealing with a not normal distribution. I can further evaluate this by looking at the skewness and kurtosis. For simplicity, skewness means if we think of that normal curve where it's got a peak in the middle, right, like a hill, skewness is talking about where that hill is. If it's a hill on one side or the other, then it's skewed. Kurtosis is talking about if we have a tall, skinny hill or if we have a low, flat hill. And these are both kind of outside of the values that I would hope to see when looking at skewness and kurtosis. And 1, I believe, is what we're looking for in skewness, and 3 for kurtosis, and those are both outside of that. And we can see that for the female distribution as well. The mean is 3.7, the median is 3.3. Those are a little bit closer, but still not where I want to see them. And then skewness and kurtosis are definitely not where I want them. So we have an idea that when we look at this, it's probably not meeting this assumption. We can look at this test of normality. This is quite rigid. And I never remember which one is which because we look at them both. But like the KS test, I believe, is the one that compares it to a perfectly normal distribution. So it's not very robust. Either it matches or it doesn't match. Shapiro-Wilks is a little bit more flexible. So when we're looking here at these results, if you remember, I said significant means significantly different, and that applies here like it did on Levine's. So when I'm looking at this KS test, I see both of these are showing us significant, which means that they are significantly different from normal. Same thing for Shapiro-Wilk. It's also saying significant, again, significantly different from normal. So these tests are both supporting what those descriptives were showing, where it's saying that, hey, maybe this is not quite normally distributed. So we're about to visually see that with our histogram here. So we can see that the peak is very much here on the left with much fewer values here on the right. We can go in and add the normal curve on here. And we can see that here, if this was our normal distribution, there's definitely a lot missing here on the left. So we can see from this histogram that the data definitely does appear to be skewed. Same thing for this group. These are QQ plots. This is, I would argue, more commonly used than a histogram for showing the normality. And the way that we read this solid line represents a normal distribution. When our dots fall on or close to this line, as they do right here, that shows us that it is approximately normal in that case, right? So we ideally want all of these dots to be very closely fitted to that line. But we can see here that as we move up in these values, they deviate more and more from that normal distribution line. Same thing on this one. So we can see here that these are definitely violating our assumption of normality. So before we even look for outliers or anything like that, let's address this normality assumption. And we can actually fix that by looking to our data. So if we look here at our box plot, as I showed in the PowerPoint, that little dot by itself was an outlier, right? Our data has a lot of dots. So what we have to do is clean up this data. And we can do that by changing all of these values. It's going to be extremely time consuming. So I'm not going to do it in this session. I will show how we can identify it, and I will show how to fix it, but I'm not going to fix all of them for the purpose of the webinar, but it'll give you an idea on how we're doing this. So we're going to follow that outlier strategy that I mentioned before of taking that 1.5 times the inner quartile range. The first thing we need to do is figure out what our inner quartile range is. So I'm going to go into our descriptive statistics here. Not that one. So we're going to go into frequencies. And I want my continuous variable to be in my variables list because that's the one that I need to change. We're going to click on statistics. I'm going to check this box for quartiles because that's what I need. And then I'm just going to leave it as is. I'm going to uncheck this box for display frequency tables because I do not need that. I only want to get those quartile values because that's how I'm going to determine my inner quartile range. So looking here, what I want to look at for my inner quartile range is what we call Q1 and Q3. So basically in this, that would be where it says 25 and 75. So what I'm going to do is just subtract the 75 value, so 5 minus the 25 value, so 1.8333. So my interquartile range is 3.16 repeating. So I'm going to take that times 1.5, and that is 4.75. So if I go back up to my descriptive statistics here, and I'm sure I'm losing some of you, and I apologize. So what I'm going to do here, I'm looking at the minimum and maximum values. And I'm actually going to rerun those because this one has it separated out. I'm just going to pull those again. For the entire variable together as opposed for each group separate. So we have our minimum 0, maximum 30. These numbers aren't going where I want. Okay, so we need to take those to our quartiles. Okay, so we have our minimum and our maximum of 30. So if we look here at our quartile 1, my annotate tools, here we go. All right, so for our minimum, if we take our lower quartile, so our 25, and we subtract that 4.75 that we got when we did 1.5 times that inner quartile range, this is going to give me a negative number. My minimum value is 0. So I won't have any outliers on the lower end because that extends past the values that I have. So if we looked at our graph, we knew that our outliers were up on the right side. So this is okay. So we're going to then take our 5 and add, because we're extending to the right, we're adding that 4.75. So we're going to have 9.75. So we're using that as our cutoff. And so any value that's above 9.75, we are going to change in our data set. So again, I'm going to show you how we can do this. And honestly, there's probably a fancy way of going in and using some of these tools where we could quickly change all of them at the same time. Work with a coach on that. Again, I think that it's going to extend past what we're doing in here. So we're looking for that 9.75, which that's a lot of these. If you look at this portions of fruits and vegetables values, anything larger than 9.75. And I love that they have these all in order. So this one, we would change to whatever the value is right below it that fits. So this is called Windsorizing, by the way. It's a specific strategy for dealing with outliers in a data set. And apparently I jumped down way too far. My data set's really, really big. That's why I used it. because it's a large data set. Okay, so we're getting closer. Okay. All right. So 9.67 is the last one that fits. 9.83 exceeds that 9.75. So we want all of these data points to be one higher. So we'll leave the 9.83, and everything else we're going to change to 9.84. So I'm changing all of these. And again, I would have to do this to all of it, and it's very time consuming. So we're just using that same value for every single value that exceeds the limit that would be considered our cutoff for our outliers. And I don't know, Excel has a really fancy way of doing this. Maybe I should have just put this over in Excel and done it because it'd be faster that way. But you can just go in and change those values so that they all meet that. And then we would rerun that test so we can see if our data is now normally distributed. I will tell you that if I applied that value to all of them, we would see that the data absolutely is much, much closer to approximately normal. It is still going to have a slight skew on the upper tail end, but it's not as extreme as it was, and it's enough that we can say that the data meets that assumption of being approximately normally distributed. Let's see. I want you guys to be able to see what this looks like, and I'm trying to do it as efficiently as possible. This is going faster. And as with every assumption, if you choose to Winsorize your data, you would explain that. So you would run the test and show what the test showed without any cleaning of the data. And then you would need to explain what you did as a result of the assumption being violated. And you would explain that you Winsorized, you would explain the process that you used to Winsorize. And then you would, again, rerun those assumptions. Okay, we should be good now. So you would rerun those assumptions. And show that the data now meets the assumption of the test. All right, so if we look here, the mean is 3.36, the median is 3. Those are closer than they were before. Same thing here, 3.6, 3.3, a little bit closer than they were before. Our test of normality is still saying that this assumption is violated. Again, these are really strict. And this is why we don't just use a single measure. If we look at our skewness and kurtosis, we can actually see that those values look a lot better than they did before, and actually are not violating. So based on skewness and kurtosis, it does appear that the data is approximately normally distributed. And if we look at this graph here again, so I'm double clicking to open up this chart editor, by the way, and then just selecting this little curve icon here to add that normal curve to the graph. So we can see that the data looks a lot better here with that curve being there in the middle, a little bit more so and a little bit more balanced to the sides. Now, we do have some values that far exceed that curve, right? So it's definitely not perfectly normal. But again, the assumption is that it's approximately normal. And if we look here at these QQ plots, here we can again see that it does deviate from that normal distribution line as we move towards the right tail. But it's definitely not like it was before, right? When we had these lines before, there's a much bigger deviation. So with this Winsorizing, we did address some of that normality deviation there. And then if we look here at our box plot, we do not have all of those extreme outliers. It does still show a few, and this is because it's separating it by group now. So we could go in and clean up the data even more to try to address these But the more that you do to the data, the more that it no longer fits the original data, and you risk substantially changing what your data was going to show. So there are risks to every cleaning method. Again, that's where you do your research and see, what are my options? What are the risks of those options? Do I want to do this?
Rachel,
So, yes.
can I pause you there?
Yes.
Just two questions.
Okay.
This Windsorizing.
Okay.
The question is, first of all, can we spell Windsorizing? Is that located somewhere in our SPSS?
No.
Okay, that's fine. We can Google it.
It is WIN as in Nancy, S as in Sam, ORIZIN G.
Windsorizing. Thank you so much.
And it is if you go to the SAGE database, if you go in there and you download the student guide, it talks about Windsorizing. It does not go into the process of Windsorizing, but it does tell you what data set in the database you can pull that does include the steps for Windsorizing. It has to do with, it is the one on cleaning, of course this is upside down. It's the one on cleaning the data.
And that was actually the second question too.
Yes.
I'm sorry. Do you have something else to add about the cleaning the data, please? I apologize.
Yes. So it does in the guide for the independent t-test, the one that I referred you to, that you can pull to do the exact same thing. It talks about Windsorizing, but doesn't go through it, but it does tell you another guide that they created that does go through it. And if I'm being honest, I don't even think that one's that great. But I have demonstrated it, and hopefully it clarifies a little bit. And again, I do encourage you, because I know a lot of this is probably more than you've had to do in any of your courses. So I do encourage you to reach out to the Academic Success Center and work with a coach for guidance and support with doing this stuff as well.
The other question, Rachel, which I'm hoping we have time to kind of like just do a general explanation, especially if this is for someone who's maybe never done stats or did stats like maybe 20 years ago, like myself. What is cleaning the data? What is that? What does that mean?
So our data, as we get it off of our surveys and things like that, that is what we call raw data, meaning that it has not been manipulated in any way, shape, or form. In the real world, you will probably never encounter this unless part of the purpose of the assignment is to teach you how to clean data. You will probably never ever encounter this in your statistics courses, because they give you data that's already clean and appropriate for doing the test. You learn about the assumptions and things like that, but you don't really practice having to go through and check. In the real world, you're almost never going to get data that doesn't need cleaned in some way, shape, or form. Generally things like missing data. So maybe somebody opened the survey, started filling things out, and then lost internet connection. So they didn't fill out the rest of it. So you have, things like the demographics, but then nothing else. Or maybe somebody had a typo. And so maybe it said, how many hours of sleep do you get at night? And they said 27. Well, there's not even 27 hours in a day. So they obviously don't sleep 27 hours a night, right? So there could be errors in the data where it was a typographical error, whether it was on the participant's end, the encoding end, who knows?
That makes a lot of sense. Thank you so much.
You also
Rachel.
would be looking for things like if you have a bunch of Likert type items, did they go through and mark the exact same number for all of them just to say that they did the survey? So cleaning the data entails a lot of things, but it's making sure that the data that you use for analysis is as free from errors as possible.
Thank you so much for that explanation.
Yeah.
That's it for now in terms of questions in the chat.
Okay. All right. So even though we do still have a few outliers and our data is not perfectly normal, the assumption is that it's approximately normal. And our outliers appear in our two groups more so than the data set itself. So we will go ahead and proceed with our analysis. So we are doing an independent samples t-test. So we are going to go to compare means because that's what we're doing. Remember, we're comparing two groups. So we're going to go to compare and we are going to the independent samples t-test. We're going to click on that. Our test variable is asking for our dependent variable. You have to love SPSS and its lack of consistency. So here for our test variables, this is going to be our dependent variable. And then our grouping variable is our gender. We do need to define our groups. So if you get to this point and you don't know what your data values are for your genders, you need to close out and go back to your data set. So ours are 1 and 2. So 1 was male, 2 was female. So we put those values in here. Just happens that those are the default values. So I don't actually have to change anything. But if you used like 0 and 1 or some other arbitrary number combination, you could put those in here. All right. We don't really do anything with these. Bootstrapping is an option for dealing with violations of assumptions. So if that was an option, then you would definitely need to go in and set your bootstrap parameters, but we are not doing that. I am going to leave the estimate effect sizes box checked here. Depending on what version of SPSS you're using, you might not have that box, and that's okay. So we are going to run our test. This first box is our group statistics. This is just descriptives. It's giving us the mean and standard deviation for each group. It's not super important to interpreting the test. Anybody that's been a good listener and taking studious notes, you probably realize we did not talk about the assumption of homogeneity of variances because it's coming right now. In SPSS, that test is actually built into the t-test. So I don't have to do anything separate. I just run the test. But before I even look at my test, I'm going to look at the Levine's test first. So that is this little box. I'm going to grab my little annotate tools again. So that is this box and this box only. So if you remember, we talked about significance. So we're going to look at that here. Significance means significantly different variances, which I don't want. My assumption is that the variances are approximately equal. So if I look at this value, 0.757 is absolutely not smaller than 0.05. Therefore, I can assume equal variances, which means when I read my test, I'm reading across the equal variances assumed row. So when I report my test statistic and p-value and things like that, I am going to be reading and reporting from that top row. The second row would be if the variances were not equal. And then this last box is our effect size. So for the t-test output, that's really all of the output. So what we care about is what I circled here. So the T and degrees of freedom. For our significance, again, your SPSS might not show both of these values. It might just give sig and then a value below it. If that's the case, it's giving you the two-sided P. This is important if you're familiar with hypothesis testing. There's one-tailed and two-tailed tests. So this now allows you to interpret both without having to do an extra step. Again, if you're not familiar with one-tailed versus two-tailed and determining which one to use and things like that, we do have a hypothesis testing group session that will be a great introduction to those concepts. You can also just work with a statistics coach to better understand those as well. We're going to go with the two-sided P for our example today. So I need to pull these values. So when I report my results, I would have my T with my degrees of freedom in parentheses equals, and then that T value, so negative 5.972. And then my P And I'm just, because mine is so small, I'm going to report it exactly as SPSS showed it to me with 0.001. If my significance, maybe it was something like 0.007, I could report P equals 0.007 instead. Again, depending on what SPSS you have, it's possible that you might still have a version where it reports 0.000. If you see that, do not say P equals 0.000. Say P is less than 0.001. Because I can assure you that the probability is not 0. Why? Because that would mean that the probability was impossible. It didn't happen. And that's obviously not the case. In this case, it's highly significant, right? So we do not want to use 0.000. We want to say it's less than 0.001. So if I was going to write up a results section for this, and not an entire section, if I was going to state the results of my test, let me get rid of my annotations here. All right, let's make my font size bigger so everybody can see it. So I might say, and I'm going to regret making this full screen. That's okay. I'll pull it back. All right, so an independent samples t-test was conducted to determine if there is an, or let's say we'll say if gender has an effect on the number of portions, portions, not proportion, portions, the number of portions of fruits and veggies that people eat. So I'm just going to say what I did and why. And then the results of the test indicate that. And let's see. We know it's significant. So the mean for females was 3.6. The mean for males was 3.3. So females eat more. Females consume more portions of vegetables than males. And here is where I want to include T and then my statistics here. So we've got 9877. That's my degrees of freedom equals. And then we're going to put in our negative 5.972, comma, P less than 0.001. We could even expand on this if we wanted to, and we could include like the mean and standard deviation in here for each of our groups. So we can include the mean and standard deviation for the portions of fruits and vegetables eaten for each group. So like females, I could say the mean equals, not what I meant to click. All right, so for females, that was 3.6, and we can round, so 3.65. And then our standard deviation. Females was 2.31. So we can include those values in our little write-up as well. There's a lot of flexibility. The biggest thing is that we want to make sure that we are including this information. And I will go ahead and stop there because I know we're close to time.
Okay, so even just your last section of how to write out statistics is something that I probably would have gain some value from. And I hope our audience members, as they take a look at that, when they're completing their assignments, they can use that as a reference. I know we have some great resources as well too, but sometimes it's just nice to see it somewhere else as well. Couple of questions in the chat about how a student would schedule a coach through the ASC in relation to stats specifically. Just so you know, Rachel, I popped in a lot of information in the chat, but I was hoping for the purposes of this recording, you could just explain some of the options for students as they are looking for stats assistance.
Yeah. So you can go to the Academic Success Center. You can get to it from your NCU1 homepage at the top where it says Resource Centers, and then click on Academic Success Center. And I'm sure that Emily probably linked our website already. But you can go to the Academic Success Center. So there is options here. I personally recommend using this one, which is our ASC chat. You can see chat is online right now. So you could fill in these boxes here and click on Start Chat. It's going to connect you to a chat coach that is online, and you can just let them know that you want to schedule a session with a statistics coach, and they would be able to help you with that. If chat is not online, we do have our chat hours. If it's offline during these hours, it just means that we had a meeting come up or something like that. You can reach out to us using other options. So you could submit a question. That would be my next recommendation, would be to submit a question. And basically you would just fill out this form. Of course, it's being slow. There we go. With what you're wanting. So you could say that you're looking to schedule a session with a statistics coach, and someone can get back with you on that. I recommend chat over the ticket because with chat, you're getting immediate support. With the ticket, it's going to take some time for somebody to respond to it, and then you get to respond back and things like that. And these sessions get booked quickly. So if someone says, oh, these times are available, and then 2 days later you get back, those might not be available anymore. The other option is to go to the coaching scheduler. So when you go here, typically individual sessions you won't see as available. My view is going to look a little different than yours, but the important parts are the same. So if you see a white space, that means it is available. You can click on it. You can schedule that one yourself. For individual sessions, more often than not, you're going to see is that darker blue color. I say darker blue. It's not the dark blue in the background. It's what I would call like a royal blue. I don't know. But that blue indicates that you can't schedule it. However, that doesn't necessarily indicate that it's not available. So for individual sessions, you might need a coach to schedule it for you. So like this white space would be white to you. That is an individual session. You could schedule it, but you can see that is with a writing coach, which isn't what you want if you want statistics. So you can see where our statistics coaches are in this list. You can also use this handy little filter here and go down and just choose statistics.
Nice.
And it's going to filter the results. So now it's only showing sessions that will give you statistics support. So if we look here, like here is an individual session with somebody that can help with statistics. It is white. So you could click on it and you could schedule that one yourself. If we went down to Sunday, you would see this 2 o'clock appointment as blue, which would tell you, oh, it's not available. But I don't see it as blue, which means it is available. So that's an example of why you might want to use chat or reach out to us to schedule, because we can see sessions that you see as not available that to us are actually available. So sometimes you'll see them as white. Typically that means that it was a cancellation or something like that. But most of the time they're going to be unavailable for individual scheduling. So you can jump on, schedule it yourself. You can reach out to us using chat, or you can submit a ticket to us and we can help you get squared away.
And Rachel, I appreciate that. I did also send the kind of the group sessions that are on the Commons calendar. I sent those as well too.
Yes.
So
group sessions, you can always self-schedule. If you want to sign up for a group session and it's blue, it's because each session has set number of students that can register for it. So blue just means that all of the seats in that session are already booked. You can see if that session's offered. We have like 2 or 3 that are offered twice a week. All of the others, it's only once a week. It's always the same time every week. So if it's already full, you can wait and schedule for the following week, or you can reach out to us and we can schedule you for an individual session instead, or see if there's another way that we can get you that support in the time frame that you need it.
Yeah, some of those group sessions like Introduction to SPSS, Demystifying Statistics. There's a lot of great sessions on there. From a group standpoint, for to assist our students. But the other piece too is obviously asking for those one-on-ones through the ASC through the ASC chat function. Yep. So yeah. I do want to say, Rachel, several people said thank you so much. They learned so much in this session. This has been very helpful. They appreciate you. I got some private messages as well too. So thank you for coming to take the time, Rachel, and to move through what can be complicated for some students. If I'm speaking honestly, it was complicated for me. But it was a great learning experience, and I'm still happy to know that my knowledge in SPSS and statistical knowledge will help my research endeavors, whether I do quantitative or qualitative, right? So yeah, appreciate that. And Rachel, anything else in closing at this point?
No, I know it was a lot and I know it was fast. So like I said, if you have questions or if you just want to take a deeper dive, like Emily said, it is recorded. So you can go back, and because you can go and download the data set, you can download the student guide, but you can download all of that materials yourself as well. You can go back to the recording and you can pause it and do it and then go back, right? So you can get more out of it if you need to, if you felt like I just got left in the dust. It is recorded. You can come back. You can ask us for questions. We can schedule a session. We can get you more support.
Awesome. Thank you so much, Rachel. And as always, for all of our students, we're always looking at ways that we can provide resources, tips, suggestions, maybe a few tricks along the way of how to be more successful in your academic journey. So don't hesitate to reach out, and we are here to support you. And until the next time, I hope you all have a great rest of your day. You take care.